Okay, this is the lab on static and kinetic friction. So in this experiment, we're going to do two experiments in one. Our goal is to calculate the coefficient of static friction, mu sub s, and the coefficient of kinetic friction, mu sub k. Okay, so we know the force of static friction. So static means it's not moving, but at the point when it just starts to move, that's what we call the starting friction. And that's given by F sub s max equals mu sub s times the normal force. Okay, so our static friction, our maximum static friction is when it starts to move. And our normal force is simply going to be the force that the table pushes back up on the box as the box sits on a table. In this case, it's equal to the weight. So the normal force is the mass in kilograms times the acceleration of gravity in meters per second squared. That gives us our units in newtons. Okay? So for the first part of the experiment, we're going to use a force sensor. And we're going to have this box, and we're going to add some weight into it. In this case, we're going to add a 1/2 kilogram, but we also have to include the weight of the box, so that number will be included in the data. So our total weight, our total mass in kilograms times 9.81 meters per second squared will give us our total weight in newtons. Okay, so to collect the data, we are going to use this force sensor here, and we're going to pull the box, okay? So I'll show you here first. So we're going to gradually, I'm gradually increasing the force on the sensor until it starts to move. All right. Okay, now I'll go ahead and show you that on the program as well, if you can see it. Okay. All right, so we have this peak here. This is when it started to move, somewhere in this value. So that's going to be our maximum peak static friction, which here it's reading as 2.787 newtons. Now, at this portion, it was moving. There's a few bumps there. That means there's a few inconsistencies in the table. But we can, when it's moving, we can also get our static friction, our kinetic friction, excuse me. All right, so we will be able to collect that as well. So our static friction, our peak static friction value for our first child, first mass, can be recorded for trial 1. And then we can also, and that's our first data table. We can also simultaneously record our kinetic friction here from this portion of the graph when it's moving. And that's our second data table. Okay, so that's how we're collecting that data. So once we collect all of our data, 3 trials at 5 different masses, we're going to make a plot. We're plotting our peak static friction on the y-axis and our normal force on the x-axis. The reason we chose that is because when we solve our friction equation for mu sub s, the Greek letter mu, by the way, for our coefficient of static friction, we get our maximum static friction over our normal force, which is really our rise over our run. So that is going to directly, if we plot it correctly, our slope will directly give us our coefficient of static friction. Now, isn't that nice? Okay, now we're going to do a similar thing for kinetic friction. All right, we're going to plot our values of force of kinetic friction on the y, normal force on the x. Our slope will give you your value of your coefficient of kinetic friction. Okay, and just a reminder, static means it's not moving. Kinetic, the root word kina, means motion, so that means motion. So friction of something not moving, friction of something moving. So kinetic friction is often called sliding friction because it's usually something sliding on a surface. Okay, so that's the first part of our experiment. So our goal is to calculate our coefficients of kinetic friction for a static and kinetic. Now we're going to do kinetic friction again. We're going to use a different method. We're going to use a motion detector instead of the force sensor. So what we're going to do is just slide our box in that direction towards our motion detector and let it slide to rest. So we're going to give it a push and let it slide to rest. And since it's our velocity vectors in that direction, our friction is opposing that motion, so our friction of our kinetic friction vector is in that direction. Okay? Now we can solve that using Newton's second law. So what does Newton's second law say? The sum of the forces equals the mass times acceleration. Okay, and we're talking in this direction here. So in this case, kinetic friction is the only force acting on it. That's after our hand has let go of the box. That's when the problem starts here. I mean, that's when we start analyzing the problem. So force of kinetic friction, and recall the force of kinetic friction is mu sub k times the normal force. So we can rewrite that as mu sub k times the normal force equals mass times acceleration. As we recall, the normal force is mass times the acceleration of gravity, so we can rewrite that. And if we look, our masses can cancel, so that's nice. We're left with this result, and to solve for mu sub k, which is our goal, it's simply our recorded acceleration from the motion detector divided by the acceleration of gravity. Okay, so let's do a trial on that. Alright, so we don't need the motion detector in this case. So there's our we don't need the force sensor, I'm sorry. And there's our motion detector, here's our box. So let's go ahead and do a trial. Okay, so I let it slide to rest. Let's do it again. Okay. So we'll go here and look at our graph. So it's pretty small, so we'll scale it up. Okay, so what we have here, this is the portion of the graph where I pushed it. We don't want that data. We want the data after my hand let go of the box and it's slowing down. So that's this portion. So notice we have a velocity time graph. We're trying to find acceleration. So that's our slope of our velocity time graph. Okay, so we can get a value here, 3.053 meters per second squared for this particular case. And that's how we record that data. Okay, so with friction, the only force acting on it, that's the only acceleration recorded. And this is in the horizontal direction. Okay, so we can record that and we can calculate the coefficient of kinetic friction. And since we have, so there's a few things we want to do here. We want, at the first part of the experiment, we want to look at our coefficient of static and kinetic friction. Should they be the same? Well, no. Should they be similar? Maybe. Now, which one is larger and why is that the case? That's something to think about and write in the conclusion of your report. The second thing we want to think about is, well, we calculated the coefficient of kinetic friction here using two methods. Are they the same? Should they be the same? And if there's any differences, what could account for that? Okay? And those are also things that should be talked about in detail in your conclusion. All right, so that is static and kinetic friction. Thank you.